This lesson deals with a high-frequency model for a JFET. You can find these notes in the ECE302 ebook in Chapter 10, starting on page 35. Let's first take a look at the N-channel JFET. So we have our symbol, and all the currents are defined entering the JFET. We'll take our previous model, which had a controlled source with 3 different expressions, and we have a diode between the gate and the drain, and between the gate and the source. What we're going to add now is the capacitance associated with these diodes, and also some resistance for the leads. I'll be calling this terminal here the drain prime, like we did for the BJT, and the source prime, and here's the drain and source from our previous definition. And what's odd here is there's no resistor for the gate. Just labeled this as just a gate by itself. I believe the reason for not putting a resistor here is that these 2 diodes are reverse biased. There wouldn't be virtually any current coming in here. But when you look at an AC model, you have this capacitance. This is the reverse bias, so it's an open circuit. And so that resistance would have an effect. In fact, we'll see this in one of the examples. I believe this is a mistake in the SPICE program as an omission. The equations for the 2 diodes are just a Shockley equation with the same value of eta for both of them because the size of these 2 diodes is about the same. What's different is the expression for the current. We have our current for cutoff, ohmic, and saturation, same equations we had before, except now there's a term multiplying this and multiplying this. This is going to be a fairly small number, and so it's going to have a small effect on this overall value of current. And what this is going to do is put a tilt in the line, just like we did for the BJT with the early voltage. We have capacitance associated with each of the 2 diodes, and they're primarily reverse biased. I showed the reverse bias equation. There's a transition between being forward biased and reverse biased. In fact, there is a forward biased model, but we're not normally going to operate the transistor that way. Those are the same equations we had before for a diode or a PN junction. I should also point out that there is a resistance in parallel with each of these 2 capacitances, which is not part of the physical circuit, but is part of something in the program so they get convergence. And that's the term 1 over G min. The model for the P-channel JFET is shown here. The same symbol we had for the P-channel JFET as before. All the currents are entering the transistor. We'll have a drain and a source with a prime because we're going to add these resistances, and then not show the prime here because there's no resistor included. You can add one. In fact, I recommend that you do that. Exactly the same model we had before. All the directions of current in the model are still shown in the same direction. Every voltage and every current is reversed in the P-channel device. If we go back to the equations on the previous page, we'll simply replace every voltage and every current with a minus sign. I've marked these in yellow. Likewise here, 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 here. There was a minus sign here, but because the pinch-off is still the same sign, we don't need to change this one. And likewise here and here, and then likewise here and here. Very easy for a computer to do, but not so easy for a human being to do. But if we're going to compare to SPICE, these are the formulas that it's using. Next, we need to convert our equation notation to SPICE notation. Some of the terms in these equations are the same as before. We discussed in Chapter 4. We had I sub s, eta, k, and v sub p, the corresponding SPICE notation and the corresponding default values in the units. What's new now is lambda. It's actually spelled out in SPICE. It has units of 1 over volts because it's being multiplied by a voltage. It needs to be dimensionless for the current equation. We now have some series resistors. R sub d and R sub s are called Rd and Rs. They're defaulted to 0, so you can see what the effect of not having them in and having them in on your circuit. The term C sub GSO, this is the value of capacitance when the voltage across the diode is 0, is called CGS in SPICE, default value of 0. Likewise, one for the gate to drain, default value of 0. You can see what happens if I had a perfect transistor. Barrier potential associated with the reverse bias capacitance, called that PB previously, has a default value of 1. Then the grading coefficient is called M. SPICE, the default is an uppercase M, although PSPICE will take upper and lowercase letters. Default value of a half, dimensionless quantity, it's a power. The term lambda, if you take its reciprocal, is the same as an early voltage. I'm going to give a tilt to the curves. You can find more about the models in our reference text, Rashid, on pages 289 to 293. I took a model for a 2N3819 N-channel JFET from the PSPICE Student Editions library and shown it over here, and it has a lot more terms in it than we talked about previously. In fact, I've highlighted these in yellow, and they are beta TCE, VTO TC, and XTI, and they model temperature effects better. In our model, we have a diode here and a diode here, but in the SPICE model, there's actually 2 diodes here and 2 diodes here, just like the BJT. And those extra diodes have these terms, ISR, NR, alpha, and VK. And just models the VA characteristics better. There's a term FC here, and when you multiply that by the built-in barrier potential, you can calculate the transition between forward and reverse bias capacitance. Lastly, there's two more terms here, KF and AF, and they actually model transistor noise. Let's take the circuit we had in Chapter 4 for VI characteristics, and let's run it with this more extended model and see what we get if we were to plot I sub D and VDS for different values of the gate source voltage. You can see we have a spacing of curves like we had before because of the square law equation. But if you go to this point here, which is the gate source equal to 0, and the drain source equal to the negative of the pinch-off, which is a minus 3 or plus 3, this would be the term IDSS. Now if we go back to the first page that we started with, that would be this equation here where we're setting the gate source equal to 0. We'd have K times 1 plus lambda VDS, and then times the pinch-off squared. The minus sign would get squared. This is a pretty small term. It's around 2 milli or so, and the drain source voltage was around 3 volts. This won't have much of an effect, but if you just take this term times this term, you could roughly predict the value of IDSS. And that's what I was showing on page 38 over here. But again, just sort of in the neighborhood of that. And that's because we have extra terms in our equation. To include all those equations would make the model really, really complicated. And it's just minor improvements in the values of voltages and currents. And next, let's take a look at the AC small signal model for high frequencies. Take the model we had before, which had just a controlled source and a gate source voltage. And now we're going to add the series resistors in the drain and source leads. And again, there's nothing here, but I would recommend actually adding a small resistance. Let's leave it off for now and we'll see what happens on the following pages. Let's add a capacitance for each of the two diodes. And now we're going to add a resistor because we now have a slope to the curve. In the program, it's taking the reciprocal of that resistance and showing it as a conductance. Let's calculate GM as we did before. In Chapter 5 on page 23, we took the partial derivative of I sub D with respect to VGS and evaluated at the Q point. Now our equation for the drain current in current saturation is this expression. Let's take the derivative of this with respect to VGS. This is just a constant. It's going to show up here as K times the quantity. And then the derivative of this with the gate source in it would be a 2 in front. Then subtract 1 from 2. And then the derivative of what's inside here with respect to VGS, which is just 1, and then 0 for this term. Evaluating this at the Q point is for the value of the gate source voltage. This term here we can get from this equation. If we take this term here and evaluate it at the operating point, we have this term squared. So if we take this and divide it on the other side of the equation for the drain current, and then take the square root, we then get the expression here in an equivalent in terms of the drain source voltage and the drain current. Bring this inside, leave the 2 outside, so we're going to square this. The square of K cancels with this one, just get K. The square of this with this just gives me to the first power, and then I sub dq. This is the same expression we had before for GM, except now we've got this term multiplying our results. In this chapter on page 19, we found R0 as the change in the collector emitter voltage over the change in the collector current. Here, same idea, we're just going to take the reciprocal of that. If we were finding the reciprocal of R out, that would be the change in I sub C over the change in VCE. And the corresponding things now are the change in the drain current and the change in the drain source voltage, evaluating that at the Q point. Take our expression for the current saturation current, and now take the derivative with respect to VDS. That's only in this term right here, so this is a constant, and then the derivative of this with respect to VDS is 0, and then just 1 times lambda. So we can find this term from this equation here. This is our value of I sub D. We then divide it by K and 1 plus lambda VDS. We then get this term over here. Evaluating that at the Q point, we'd have I sub D at the Q point. The K's cancel, have a lambda, and then a 1 plus lambda VDS at the Q point. Now previously, lambda was defaulted to 0, so that would make this conductance 0 and the reciprocal infinity. So we didn't have a resistor there, and that's why we now have a series resistance for the source and drain leads. The model for the P-channel device for AC would simply be changing the polarity of the gate source voltage and changing the direction of the controlled source of GM VGS. We will also flip the subscripts accordingly like we did in Chapter 5. Lastly, we have the capacitances associated with the gate to source and gate to drain diode. We'll go to our large signal equations and grab those and evaluate those at the Q point. Now let's take this model into an amplifier. What's shown below here is a common source amplifier where my input voltage is node 2 and my output voltage is node 7. I wrote the file just like we did for the BJT example. Let's take a look at the details of that. But then what I've added is this more extended model for the 2N3819. I'm going to plot this from 1 Hz to 500 megahertz with about 200 points, or 24 points per decade. As for the operating point, so that's what's listed here. These are the DC terms, and then these are the AC terms. I also printed out the model. Again, it's a little bit easier to see when you write it out line by line in terms of the terms that we included. Go back to page 39. We can grab the formula for GM, which again has this term with lambda in it. Let's see how close we come to what Spice calculated. The value of K is the value of beta, and then our model was 1.304 milli. Then we have 1 plus lambda, which is 2.25 milli. And the voltage across the drain source is 4.92, and the value of the drain current is 2.79 milliamps. The square root of that times 2 is 3.836 millimos, and you can see here it's 3.84 millimos, very close. The drain to source conductance is here. We had this formula, so let's evaluate it. Lambda was 2.25 milli, and then the drain source voltage was 4.92 volts. And we're going to multiply that by, again, IDQ, and I get 6.209 micromos. Over here, it's 6.22 micromos. Take the reciprocal of this, it's about 161K. That's going to be in parallel with a 2.7K and another 2.7K when you put in the midband model. So this doesn't have much of an effect. That's why we didn't really consider it previously. But when you're looking at circuits that have very high resistances, especially in IC designs, this reciprocal of this term can become quite significant. In our model, we have a 1 ohm value for R sub D and R sub S, so those will be the series resistances. In our capacitance model, we have C sub GS 0, and that's this term right over here, C sub GS, and that's 2.414 pico. And our gate source voltage up here was a minus 1.54, so that minus with this minus becomes a plus. The grading coefficient was 0.3622, and the barrier potential term is defaulted to 1. That gives me 1.722 picofarads, and you can see over here it's 1.72 picofarads, pretty much exactly the same number. And then lastly, we have the capacitance between the gate and the drain, and that capacitance needs the voltage across the gate to drain. So we could take our transistor, just go around the outside of it like we did in chapter 4, and show that the gate to drain voltage was the gate source minus the drain source. Plug that value in over here. Up on top, the gate source voltage is 1.54 with a minus sign. And then we're going to have the drain source voltage, which is 4.92. We're subtracting that, and those two minus signs cancel with this one, give me a plus sign. We get M was 0.3622. And the value for this, if you look up on top, was 1.6 picofarads. And that gives me 0.7727 picofarads. And let's see what we get here in the Spice calculation. We get 0.773 picofarads. So again, pretty much the same number. The first Bode plot I have here is the plot of the output voltage over the input voltage, taking 20 log of that by putting the term dB there, and I get this result. You can see I have a midband gain of 14.183 dB. If you divide this by 20 and raise it to the power of 10, you get a gain of 5.1185. The 3 dB frequency is about 16.2 hertz and 160.7 megahertz. Phase angle plot is below, the difference between the output and the input phases, and you can see I have a negative gain in the midband frequencies. What I'd like you to do is to take the methods we had on pages 24 to 32 of this chapter and see if you can verify the results of midband gain, the 3 dB frequency at the low end, and then the high end. The calculations you get will match the Spice results. If you go back and repeat this again, but now for V out over V sub S, we were shorting V in, now we're shorting V sub S, you'll get quite a different result. And this is a high frequency model for a JFET.